So do you have anything to say, or you just...
Is there an intuitive reason why equilibria don't show up in this?
It's an extremely good question. In the Boy Scout version of the book, which we can share, but the vulgar people outside Georgia Tech and outside the group of collaborators cannot, I have a formula for equilibria. And I don't know what to do with this. So, I'll hand it to anybody who wants to. Just check out the Chaos book and you can read it. So I have the formula, and I don't know what it does. So my intuitive idea is that we're interested in dynamics. So we're interested in averaging. And equilibria don't move. So they're very important.
These don't move either.
Well, they're invariant set, but they encode time evolution. See, each periodic orbit is an invariant set, but it's encoding the time evolution on the set. So, we know that they move because they explore the turbulent regimes of our problems. So, we can literally see what they do because we can see that they're close, they never, what you see in turbulence, you see in individual periodic orbits. They capture that. So they capture dynamics. So if you have a system which is, for us, boring, but it's, often the most interesting thing. So, for example, let's call statistical physics. When you go to one fixed point, phase resistance, blah, 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 then equilibrium is very important because you just compute the average by evaluating at equilibrium, and that's it, you're done. No need to average over it. But if you have dynamics, I haven't found a good way of using the part of the trace formula that comes from equilibrium. So in this thing that I did on the web for you and in the class before, but in the Laplace transform, this quantity, I fuzzed about epsilon equals 0. I made it slightly positive. And also, when I derive this determinant, when I do it a little more seriously, I have actually a ratio to determinants in which epsilon 0 cancels out. So I regularize them. So I don't see the equilibria. They're seen indirectly because the shape, whenever trajectory comes close to equilibrium, it picks up average properties of equilibrium. So if it's a complex equilibrium, the velocity it moves around is given by the complex part. And so they're indirectly very important. But in cases I'm familiar with, and Lorentz is the simplest example, equilibria are there. They play a geometric role because they shape the whole thing, but you never visit them. You never visit the ones that you just can come close to, and you don't even visit the one that you know that you're there because you have no probability of getting there. So, I don't know, this is a very important question. I would like us to be able to use the information about equilibrium, because now we use it indirectly. We take periodic orbit that comes to equilibrium and goes away, then the one that circles it once and comes back, circles it twice and comes back. And so we use that information. So it seems like stupid. Shouldn't we just use the equilibrium itself instead of circling it 7 times? And for hyperbolic systems, it looks like you don't want to do that. Your equilibria are kind of cut out from the important dynamics. They're not part of the strange attractor. They're not connected. But, that's totally open to discussion because we know that unstable manifold are connected. It's just that it's not obvious that a stable manifold are connected. It's not obvious you can come to them, but you know that you can leave them and go, I got it. So they don't seem to be part of recurrent sets, but I might be wrong. There might be very important examples where they are. So it's also true of 3D turbulence, and it works in this crude way that if you look at pictures, so that's what people do who work in plumbing, they take snapshots of the numerical simulations. The human eye cannot discern the difference between an equilibrium traveling wave or a near passage to it. So at the level of 10%, 5%, 10%, etc., estimates of dynamics, these equilibria are very helpful. they give you pretty good guesses, because it turns out these equilibria, are pretty complicated. So they capture some very complicated, entwined states of fluids and cardiac dynamics and whatever. So they're good at that level. Then when you look closely, and for that you have to go to state space, it turns out they're not part of the game. So that's, we see this in Navier-Stokes. So we use equilibria to kind of usher, put a cage around, you use the stable and unstable manifolds to put a cage around turbulent behavior. So you can see they're very important because, you seem to be just staying where they tell it to stay. They confine the stuff. But all the averages are computed on the time-dependent solutions, on periodic orbit and relative periodic orbits. So I agree they're qualitatively important until you start looking in detail. So